strong acids. Or bases. And I gave you the example of hydrochloric acid, HCl. When we shove that into water, this acid completely, almost completely, dissociates into H plus chloride ions. And because it completely dissociates, it was quite easy for us to say, okay, if we start, let's say, with a 0.1 molar hydrochloric acid, almost all of it will be dissociated. So once it is dissociated, we will have a 0.1 molar proton concentration in it. And that's the characteristic of a strong acid. It doesn't matter so much if the acid is highly diluted, like I gave you the example of a 1 nanomolar hydrochloric acid, it still completely dissociates. So that was the example of a strong acid. But what happens if we have a weak acid? What happens if the acid is weak? Now let's have a look at it first. Let's say this is our acid, HA. I write the H first to indicate it's an acid, HA. Now when I put that into water, a little bit of it will dissociate into H plus, A minus, exactly. That would be the anion. This here is the acid. This is the conjugate base. But not all of it will dissociate. Only a small fraction of it will do that. But it's not a static thing. This anion, A minus, might also grab a proton that's hanging around and it will react back to an HA. So it will go back and forth. And for this process, actually, once the reaction has happened, we can formulate that as a sort of an equation. And we can say, well, the concentration of the protons times the concentration of the anion, of the base, divided by the concentration of the acid. This is loud.
Equilibrium constant.
This is the equilibrium constant Ka. So this guy here is the equilibrium constant. And this equilibrium constant tells us to what extent this acid actually dissociates into a proton and the base. And I just want to give you a little example about that. Let's say we have an acid which only dissociates to 1%. Only 1% of this acid will dissociate. When we used hydrochloric acid, 100% dissociated. But in this case, only 1% dissociates. Can we calculate the equilibrium constant? Let's say we have a 1 molar, we start with 1 molar of the acid, of the HA. So, HA gives us H plus A minus. Ka gives us H plus times A minus divided by HA. So, we start here with an HA of 1 molar. That's the starting. That's the start. Only 1% dissociates. How much have we got of the protons in molar? Yes, we have 0.01 molar. How much of the A minus have we got? Aha, we have also 0.01 molar of the A minus. That's great. How much of the HA have we got left? Yes, 0.99 molar. Yeah, that is what's left. This is here what's left. Okay? So let's try to figure that out. Ka equals 0.01 molar times 0.01 molar divided by 0.99 molar. What would be the unit of Ka? Loud? Molar, yes, because 1 molar cancels out. And if we whack that into our calculator, what do we get? Okay, and in English?
1.01 times 10 to the minus 4.
Yes, 1.
1.01.
Okay, 1 times 10 to the minus 4 molar. So that's our dissociation constant. Now, very often, chemists and biochemists don't like these things because they, the 10 to the minus that sometimes easily gets lost. So they do the same trick as they've done it with the pH. And they define what is called the pKa. Can you imagine what the definition of pKa is? Equals minus log of Ka. Yeah? P usually, you can envisage that, P usually means minus log. So my initials are pK minus log K, minus log Klapper. I don't know whether this is a good unit, but in my view, I think it's a bloody good unit. Never mind. So what's the pKa of this thing? Exactly. So the pKa equals 4. So 1% dissociates, gives us a pKa of 4. Or in other words, if you have a pKa, this usually indicates that you have got a weak acid. Yeah? So if I give you a pKa for something, it is, weak acid. Careful. If you don't have a pKa, assume it's a strong acid and it dissociates to 100%. Okay? Happy with that? Fantastic. God, I'm so good. How can I live with myself? Now, I told you the Ka is when we put the acid into water. So let me write this again. HA gives H plus plus A minus, and that was our equilibrium then. What happens if I put A minus, this guy here, into water? Bless you. What do you think will happen? Think about it for a moment. What could happen? What happens?
Does it form the acid?
Oh, very good idea. Does it form the acid? Does it form the acid? Yeah? So, this A minus then simply grabs a proton and goes, come with me.
Good.
Right? So, it leaves the OH minus on its own. So we have HA plus OH minus. That is actually, for those of you, I hope I didn't startle you too much. That is actually why this A minus, this guy here, is a base, because it generates OH minus when it's put into water. Yeah? Can we formulate an equilibrium for this? Well, we can write HA times OH minus divided by A minus times H2O. This is another equilibrium, and we can formulate an equilibrium constant, but now it is an equilibrium for a base, isn't it? So we can say this is Kb. That's the equilibrium constant for the base production. Are you happy with that? And now we are going to do something really, really filthy and dirty. It's really, really, it's taboo. Let's do Ka times Kb. Yeah? So what did we say for the Ka if you go back in your notes? We said Ka equals H plus times A minus divided by HA. Yeah, that's Ka. And Kb, we've just done, is HA times OH minus divided by A minus times OA. My son is not here who could correct me. God, I got an earful last time when I said OA. He was furious. He said, Daddy, that's so common. Yeah, right. I will remind you next time you say WTF. Welcome to Facebook. He told me that it means. Right, Kb times Ka, or Ka times Kb. What have we got left? Well, first of all, we can cancel the HA. What else can we cancel? A minus. What have we got left? H plus times OH minus divided by H2O. Does that sound familiar? No? What happens if we can we write the chemical equation for this, what we've got here? H2O dissociates into H plus times OH minus. Remember, that was on Thursday. This guy here is called KW, the dissociation constant of pure water. Remember what the value was? 1 times 10 to the loud? Minus 14 molar, exactly. Yeah? Vaguely remember? And we can do a pKw. What is the pKw in this case? What do you reckon? Loud? 14, exactly. Yeah? But it tells us something more. This is again this magic 14. So you all know the answer to life, universe, and everything. What is that? The answer. Loud? It's 42, exactly. Can you elaborate why it's 42? It's the Hitchhiker's Guide to the Galaxy. What was the question?
What is the meaning of the universe and everything?
Yeah, what's the meaning of... Well, actually, we don't know. We've forgotten the question. Yeah? And only the researchers... Which are the researchers? Who are the researchers trying to figure out this question? Who are the researchers? The mice, exactly, the lab mice. So if I'm talking in complete riddles, yeah, Douglas Adams, Hitchhiker's Guide to the Galaxy, it will make, everything will become clear. So, for the philosophers, the answer to life, universe, and everything is 42. To the chemists and biochemists and biologists, the answer to at least a lot of things is 14. Right? So I want you to remember that. And the amazing thing is, pKa of an acid plus the pKb of the corresponding conjugate base is, what do you reckon? Is 14, exactly. Because of this correlation here, Ka times Kb. So if I, for example, give you a pKa of 5 for the acid, you can immediately calculate the pKb, which is 9, of the corresponding base. Everything is 14. Remember, pH plus pOH equals 14. Woohoo! Everything is 14. Isn't that amazing? 14 is the magic number. We cracked it. And we are not white mice. I hope, well, I'm not white. I'm not a white mouse. you get into a lot of mind games here. Yeah. So I want you to remember these things. Okay, so that was sort of just a little bit of introduction to weak acids and weak bases and things like that. But how do we actually figure out the pH of a weak acid? Obviously, we need to know how much of this acid dissociates. And if I tell you that, for example, in a weak acid, and you have a 1 molar solution, only 1% of the acid dissociates, you can figure out what is our proton concentration. And Anton did that already earlier. He said it is 0.01 molar. Sorry?
That can't be our pH because that's a pH of 2.
So that would be our pH of 2.
But that's not a weak acid.
Why is it not a weak acid?
Because weak acids are usually 4 or 5 or something like that. Because
Oh, is that right?
usually, but I'm not sure. Good.
Aha. What would be the pH if that was a strong acid?
1.
What?
1 would be a strong acid.
What?
pH of 1.
What? Okay, think again. We have a 1 molar acid. What's the pH? Everything dissociates. Remember, minus? Minus log 1 molar, so that would be 0. That was if it is a strong acid. Yeah? But if I have the same concentration and it's a weak acid, for the weak acid, it's pH 2. So, same starting concentration, strong acid is pH 0. Weak acid is pH 2. How many times weaker is the weak acid compared to the strong acid? What's the factor?
100.
100 times weaker, yeah? Because 1 pH unit is factor 10. 2 pH units are factor 100. So this weak acid is 100 times less protons than the strong acid. Does that make sense? Yeah? Okay, so that's great. If I tell you how much of this acid actually dissociates, how many protons I have. But sometimes we don't know. Sometimes we only have the pKa value. And then it gets as hairy as a badger's behind. Because you have to do something with it. Now, what do you have to do with it? Let's write it down again. If everything else fails, let's write things down. You will get a point for that or some marks in an exam. We have HA dissociates into H plus A minus. And now we write down our equilibrium, Ka. We have done that before, equals H plus times A minus divided by HA. Okay, happy with that? Yeah, not terribly difficult so far. How many protons do we have in this? We don't know. So let's just simply call it X. So we can write Ka equals X. And I do it like that, so that we don't confuse it with the times. How many of the A minus have we got? What do you reckon? How many A minus have we got? Now, X, because for each proton that we generate, we also generate an A minus. Absolutely right. So X times X. Yeah? How much of the HA have we got left? Loud? HA minus X. You are absolutely right. Bingo, spot on. HA minus X. This is what's left. Yeah? And some of the acid has dissociated, and that gives us X protons at XA minus. So that goes away from the HA, from the original concentration. Now, again, we do a little bit of a dirty trick here. And we say, actually, remember, our acid is very, very weak. So, for this HA minus X, what we can write is, this is very close, actually, to HA. Remember earlier in the example where 1% dissociated, let me see if I find that again. We had 0.1 molar here and 0.1 molar here, and then we took 1 molar minus 0.01 molar, and that gave us 0.99. So that's pretty close to our starting point, because the acid is so weak, it doesn't really want to dissociate. And therefore, we can write this close to HA. Strictly speaking, a mathematician would howl, because they say, no, 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 you can't do that. Well, we're not mathematicians. We just want to have fun. Although maybe you will disagree with my definition of fun. But so, what we can do is, actually we can write Ka equals X squared divided by HA. Now, if we had the X, remember the X is our proton concentration. X equals the proton concentration. We could very easily calculate the pH. So we have to solve this equation here for X. Okay? Let me quickly write this down again. Ka equals X squared over HA. Okay, let's start solving. I bring this to the other side, and I have X squared equals Ka times HA. Yeah, happy with that? So what is X? It's the square root of Ka times Ha. Would be nice. Usually I don't have Ka, I have pKa. And remember, the pH is the negative logarithm of x. Here is dirty, filthy trick number 3 for today. I take both sides minus log. So I get minus log x equals minus log of square root Ka times Ha. By the way, you don't need to learn how I get to this stuff. You just need to learn the end product. So if you have switched off, as I said in my first lecture, 80% have sexual fantasies. I hope you enjoyed yourself. Yeah? But don't worry if you didn't get it. If you are still in fantasy land, that's good. That's all right. No worries. So minus log x, minus log the proton concentration, we can write pH, equals. Now I do a little bit of mathematical tricksing. The square root I can write as half. Half of minus log Ka minus log the acid concentration. Okay? Minus log Ka, what's that? Loud? pKa. So what I can write is pH equals 1/2 of, and we need to put that in brackets, pKa minus log Ha. And I'm terribly sorry. Now I have to wake those up who are, in fantasy land. Oh my God, that was spectacular. I didn't mean to, impose that much pain. This is an equation that I want you to remember. pH is half of pKa minus log of Ha. Let's do a little example. Let's say I have an acid with a pKa of, let's say, 3, and I have a 0.1 molar solution. What is the pH? Well, do you want to try it yourself? Or shall we do it together? The first example we do together, yeah? pH equals 1/2 of pKa minus log of the acid So pH equals 1/2 of pKa is 3 minus log 0.1. Log 0.1 gives me -1. So I have 1/2 of 3 minus -1. That's 4. And therefore the pH equals 2. That make sense? Now if you look at it, pH equals 1/2 of pKa minus log acid. I can rearrange this equation in whatever way I want. So for example, I can find out the pKa of an unknown acid because I've got a pKa here. So what I can do is I can rearrange this equation. I bring this to that side, so I've got 2pH, 2 times pH equals pKa minus log acid concentration. Let's say I have a 0.1 molar acid concentration, and I measure a pH of 4. What is my pKa? Well, 2 times pH, that gives me 8. Well, let me do it slowly. 2 times 4, I bring this to the other side, plus log of 0.1 equals pKa. So that's 8 minus 1, that's 7. So my pKa is 7. Actually, pKa of 7, does that remind you of anything? Could be water, right? Could be water. This unknown acid. And just before we finish, I've seen something in a pseudoscience newspaper. I think it was the Daily Fail or so. And they found that dihydromonoxide is an extremely dangerous substance. It's the most toxic substance in the world. It kills most people. It has the highest mortality rate. And so very toxic. Absolutely lethal, this thing. And it is the strongest known acid because it has the highest pH. Highest known pH. Congratulations, scientist of the daily fail. I'm proud of you. And if you haven't figured it out, dihydroxy monoxide is water. So whenever you read anything, please question it. And of course, the highest known pH is 7 for an acid. So, on that note, I have sent out some quizzes for you that you can do to self-check whether you got it. There are no deadlines, and it doesn't count for your coursework, but it shows you whether you understand the principles. On Thursday, I will do a few calculations related to this pH. Go in peace, but go.